and welcome to our new lecture here on Interpretable Machine Learning. Welcome. This is the first session in our first chapter. So this is an introductory chapter in this first session here. I want to motivate the need for interpretability a bit. I want to explain why interpretability has become so popular in machine learning. We'll discuss this a little bit also in terms of use cases. I'll do this much more in an upcoming session. And I'll also spend a few minutes to talk about the historical developments until here of the field. So I guess I do not have to explain to anybody listening to this video why machine learning has such a huge potential to help in creating automatic or semi-automatic decision-making processes because of its extreme predictive performance that we have seen in the last, let's say, 10 to 15 years. So we have all become extremely fond of using models like gradient boosting, kernelized methods like radial basis function support vector machines, Gaussian processes, or deep learning neural networks. Unfortunately, many of these models are quite complicated to explain to humans, so it's quite hard to understand their global general structure or even only the individual predictions that these models produce. The reason for this is, I guess, twofold. So one is because we have increasingly used higher and higher dimensional feature spaces. So sometimes these models are applied to, I don't know, hundreds, thousands, or even millions of features nowadays. Even linear models or simple tree-based models might be hard to understand in these spaces. Depends a bit on how you're using that and how kind of much you're regularizing these models and how sparse you are making them, which is possible. But if you're using these types of techniques here, usually they come from kind of two categories. Either they are producing extremely large ensembles, like gradient boosting or random forests, where the individual models might be explainable. So for example, shallower trees. But if you create a collection of 1,000 of these models in an ensemble, obviously this is much harder to understand. Or these models are, let's say, local techniques. And with local techniques, I mean that they kind of are able to model very fine-grained local structure in high-dimensional spaces. So you can only draw this here in 1D. I guess I could try in 2D. I will not. And you have a predictive surface which might look like this, but in a, I don't know, in a 1,000-dimensional space. How are you ever going to explain this back to a human? The reason why we like these local models is because for many of these model classes we can actually prove something, a certain property of these model classes, that they might be something like universal approximators, which means that they can learn an extremely large class of different functions. Under mild assumptions, I guess we could say, given enough data, they can basically learn nearly everything, right? But they are very their decision surfaces can become arbitrarily complex, and because of that, they are very hard to explain back to humans. Another important point I think that one should be aware of, and this is something that I try to drive home pretty early on in any ML lecture that I teach, is that different applications of ML have different goals in mind. Some of these, for some of these applications, we might be mainly interested in producing a very powerful predictor. So I would call that learn to predict, learn to minimize errors. And usually this is always kind of the goal to a certain degree. But for some applications, and if we are in such a scenario where what I would call is a learn to predict scenario, we are to a certain degree satisfied with getting our hands on a model that we can use then as a potentially black box predictor, because we at the very least can empirically prove that it works very well. And there are scenarios like this, I don't know, maybe in engineering, where this might be enough. In other scenarios, I don't know, in the social sciences, maybe also sometimes in medicine, the underlying goal of the application of such an ML model is not really to create a black box predictor, it's more to understand the relationship in data. to understand that and to discover new insights or to kind of confirm certain hypotheses that you have. These different scientific domains, or I guess that the same holds true for certain applications in commerce or in industry, have traditionally relied on more on simpler models, on less complex models, which are more or less directly explainable. So linear models, trees, and so on. Many of these domains are currently quickly changing and are migrating towards more complicated ML models as well, because the data sets have become larger, data sets have become increasingly more complex, become higher dimensional, become less clean, and very often these traditional models work less well. And I guess we do not want to, or we often potentially do not want to create inference or extract inference or extract explanations from stuff that doesn't really work on your given data set. And this is why nowadays, even for these domains and applications where like learning to understand is more in focus, people are now applying these blackish or grayish boxes and these more complicated models, and they're increasingly more interested in generating explanations for these as well. I guess in general, many of these different ML models we could put on such a trade-off curve here, which trades off predictive performance against interpretability. Very often this is kind of a function of how complex these things are. So at the very end of the spectrum, we might have, I don't know, neural networks here, or even radial basis support vector machines, which very often work very well, but which are exactly for the reasons that I just outlined a few minutes ago, extremely hard to understand. And then at the other end of the spectrum, we might have models like linear models, which are simpler to explain. And then here in the middle, you might have, I don't know, shallow decision trees, deeper decision trees, ensemble techniques. And for some of these ensemble techniques, since 20 years, there have been at least preliminary interpretation techniques have been available. So all of these models here live somewhere on this spectrum. I should also say that this is a fairly strong simplification of what really goes on. I mean, a linear model or a tree can be difficult to understand and to explain if it is fitted on a high-dimensional space without any sparsity constraints. A neural network you can make very shallow. I mean, logistic regression can also be fitted with neural network software. So it depends on the hyperparameters of these models and on the specific, I don't know, architecture and model subclass that we are using. I guess I don't want to deep dive into this too much here. I guess maybe there's one last thing that I want to say, and that is in I guess every practical application, we should take a certain path through these through this zoo of models. So, and that path should start here. So we should always start with analyzing and trying out these simpler, less complex, more explainable models, and only go to the next stage if there's enough evidence that we really need that. And that doesn't necessarily mean that the next model is better, that it is significantly better. It needs to be better in a relevant sense. Sometimes a certain amount of predictive power might be enough for a certain application. And if that is the reason, if that's the case, and if one of the models up here reaches that goal, I definitely want to stay there. I don't need to go here and then incur all of the extra costs of these models being much slower, being much more complex, and being much less trustworthy. But very often we unfortunately figure out that we need this predictive power here, and then we are interested in how to explain these models. So obviously this need for explainability becomes even more obvious if we are talking about critical areas of application of machine learning where decisions of these ML models might affect human life. So for example, very often used example are credit scoring applications or insurance applications. So maybe you want to explain to a user the reasons for not granting a loan. I mean, that might be, I don't know, a life-changing decision. Fraud detection in insurance claims. I guess we want to explain to a person why we think that a certain fraud was detected here. Pretty obviously, there are also medical applications, so identification of diseases, diagnostic procedures, or even more critical recommendations of treatments. I guess all of you know that in many of these applications, even from a legal perspective nowadays, we now might be forced to provide explanations to users. So there's the GDPR, so the General Data Protection Regulation, that requires for some applications that models have to be explainable. I guess even without this legal perspective, that might be kind of an ethical right of users to have these decisions and these models that are used, I don't know, in their personal context to be explainable and to be trustworthy. So as, for example, this very, very infamous compass example here, where machine learning models were used to predict whether certain violent offenders would offend again. As we're going to look at this a bit further in one of the next sessions, I will keep this short here. And here on the last slide is a very brief, very cursory overview over the history of interpretable machine learning. So I guess we could start at the beginning of machine learning itself. We might locate that in the 18th or 19th century, when linear regression models were invented by Gauss and Legendre. And in a certain sense, I guess not only in a certain sense, we could really see Gauss and Legendre as the first machine learners, because what they did was not only invent linear regression models, but they also invented the principle of fitting models under the least squares principle. So they were already performing risk minimization. They were coming up with all of these underlying mathematical concepts. Obviously, they were doing this without a computer. They were doing this with pen and paper, but they were fitting linear models or polynomial models to observational data, and then analyzing the results. In the 1940s, there was then the emergence of sensitivity analysis. Don't want to deep dive into this too much here, but what I want to say is that sensitivity analysis is a very, very related field. So what are we interested in sensitivity analysis? So that field usually looks at either technical, very often technical or technical processes, or physical processes, or certain surrogate models that we have used to approximate these processes, and then it tries to figure out how certain inputs act on the outcome, which of these inputs are important to reach a certain outcome. And that sounds a lot, if you already know a little bit about interpretable machine learning, this sounds very, very similar, right? And many different concepts have been studied and invented in sensitivity analysis and in interpretable machine learning, sometimes under different names, sometimes even with the same maths, or sometimes even very related formulas. And I guess the two fields can still learn quite a lot from each other. In the middle of the 20th century, then rule-based machine learning techniques came about. So decision rules, decision trees. There was this very, very famous book by Breimann about the CART algorithm, so classification and regression trees. I think that was 1984. Hope I'm not 1 or 2 years off here. And then Breimann also invented the random forest a couple of years later. And pretty early on, when the algorithm itself was invented and published, they were pretty quickly built in feature importance measures for random forests, and then things like partial dependence plots came about for ensemble techniques like forest and boosting. And in the last decades, we have really seen interpretable machine learning, IML, or XAI, if you want to use that terminology, as an independent field of research, with really hundreds of papers being published about this. And I guess now every new month a new method is being proposed in that field. And then around 2005 or 6, we had the deep learning revolution. And now people are obviously also interested a lot in explaining these very, very complicated models, especially also in the field of computer vision. So there are also now specialized XAI techniques for convolutional neural networks and so on. So I'll keep this at that point here. I hope you enjoyed the first session. See you in the rest of the lecture. Yeah, bye-bye.